4 minutes? I thought I had 15 minutes. My students told me that professors are simply unable to talk for less than 15 minutes. That's the slot I have. So they encouraged me to make a video, and that's what I'm going to show. So when it's over, I should stop as well. Let's continue the themes of the morning: structure, motion, and biology. And then we'll add the twist that we put on it from our lab. If we could have the video, the lights down. I solve mystery stories from nature. That's my job. And my lab at Berkeley studies the motion of animals with lots of legs. And what we do basically is we run animals on treadmills like we do humans. That's a human. That's not a human. That's a cockroach. When we do this, we measure things. Here we're measuring the energetic cost of locomotion of an animal to see how much energy it uses. In fact, we're giving it a stress test. We're measuring its maximal oxygen consumption as it's running. In addition, we want to quantify motion, the motion being the kinematics and the forces involved. 6 legs, 44 legs, 8 legs, and biomechanically what seem to be too many legs. This is a giant African millipede that we've looked at. Look at the waves as they move forward. Now what we do is we take these animals, and this one is a cockroach, we're running it over a glass plate. And what we do is create 3-dimensional spatial models of its movement. And we do it by 2 high-speed cameras that can capture 1,000 pictures in 1 second. And then we're able from this to quantify the motion of every joint in terms of velocity and acceleration. In addition, we need to measure forces, the kinetics, how you push against the ground. And we did that by building the most sensitive, fancy scale. Here it is. It measures the forces of the whole body of the animal as it runs over it. But what we'd like to do is measure the forces of every individual leg of things as they push on the ground. So we had to develop something else. We developed a photoelastic track where we put this photoelastic material between 2 polarizing filters, and we shine light up from underneath into our high-speed cameras. As the animal runs across the photoelastic material, it stresses it, and light emerges. The larger the spots of light, the greater the force they develop. The photoelastic material is Jell-O. The first time we did it, it worked, except we used orange-flavored Jell-O, and the animal stopped and began eating the apparatus. Now we use unflavored Jell-O, and it works fine. The next shot is slowed down 30 times, and this is an animal executing a turn, and we can quantify it now completely. Why do we do this? Why do you study the performance, the energetics, the dynamics of animal locomotion? We do it for 3 reasons, being a professor: roots, rules, and relevance. We do it because roots, we care about the origins of organisms. How did they get to be the way they are? Their evolution. And we care about rules, about how they work. How do their muscles function and their nervous systems? Those 2 make up the heart of basic research, roots and rules, and that's what we do. But we also care about relevance, relevance to humans, organisms, as well as the environment. Now you might also ask, why do we study these crunchy animals with lots of legs as opposed to soft, squishy animals like leeches or maybe humans? Well, we selected these animals not because we like them. Frankly, they're disgusting. However, they can reveal nature's design principles. As Krog's principle predicts, they are the animals of choice when we want to study locomotion. They're easier to work with. They're simpler. We believe that diversity enables discovery. So for examining a variety of animals, we can learn lessons of design from nature, in our case, general principles of locomotion. For hundreds of years, many naturalists have argued that each of the animals move differently in their own special way. And only recently could we quantify this, could we test it. Others have argued, like Sir James Gray, that maybe these many-legged animals move like wheels, kind of like a couch on coasters where they have a smooth ride and don't speed up or slow down as they move forward. A reasonable idea. Well, here's what we found when we actually made measurements on these animals. Here's an animal running on a treadmill. Watch it carefully. This is a crab. What you'll see is this animal, as it moves with each step, slows down and speeds up. In fact, if you look at it really carefully, you'll see that it's in fact bouncing up and down as it moves. That's not different from how you run. It turns out that we've discovered that all-legged animals act as pogo sticks. And that's a general rule. Now, we can't call them pogo sticks. We call them dynamic spring mass models, of course, where the body is the mass and the springs are the legs. And what we've discovered is that 2, 4, 6, and 8-legged animals all move in the same way. They all bounce along on a virtual spring. In each case, 2 sets of legs propel the body alternately. A set being 1 in a biped like us, 2 in quadrupeds like dogs and lizards, 3 working together in something like an insect, and 4 working together in something like a crab. Let me show you this. Here's an insect running along. Now watch its legs very carefully. You'll see that 3 move together. And they alternate with the other 3 in a nice tripod kind of arrangement. Those 3 legs sum together to work just like one of your legs. You can't tell the difference. Now you might say, wait a minute, this animal isn't running. It's bouncing on, but it's not leaving the ground. It's not in the air. But it is running. But it's running like Groucho Marx, with bent legs. In fact, Tom McMahon at Harvard has shown that leaving the ground isn't a requirement for a running gait. It's a bad definition. And Tom even defined this gait by a dimensionless ratio that we call the Groucho number to characterize this situation. Now, does that mean that many-legged animals never leave the ground when they run? Is that what we're saying? This is the animal you think you don't have in your kitchen. It's the American cockroach. It is a tremendously fast runner. It's less than an inch long, but it can run at speeds up to 5 feet in 1 second. So you never see it. As a joke, my students put this in the Guinness Book of World Records as the fastest insect. And you'll see that run coming up next. The fastest an insect has ever moved. There it is. Now notice what happens when it does it. It actually lifts itself up and runs on its 2 back legs. It becomes bipedal. How fast is this? If we scale it up, like ABC News did in their Olympic coverage, to Michael Johnson, we can race it. Here's the race, 200 meters. It's over. The cockroach easily wins this race. It goes 50 body lengths per second, or 200 hours. Now, you might then ask, the wheel idea was good. Are there any animals like wheels in nature? That's a reasonable question. Here's the closest thing we found. It's a shrimp-like animal. It moves this way. It's lying on its back, and that's how it moves on the beaches of Panama. Very few people have seen this animal. This is an incredible creature. They're not just found in your imagination or Escher prints. They're out in nature. And this is important because if we don't preserve their habitats, we'll never find things like this again. Extremely important. Now, what does this mean? We use this information to understand what produces movement, muscle function, and nerves, and how they work together. The answer is we can do that. Here's an insect. It's lying on its back. I'm pulling on its leg. Look at its leg carefully in its structure. I ripped it off, no problem. They grow back. It's a great animal to use. Now we produced here a 3-dimensional musculoskeletal model. Now what's important about this isn't just a cartoon or even a static structure in 3D. This, like John Gage mentioned, has the physics built in. So we can actually do experiments on these cyber muscles to understand precisely how they function in the animal when it's running. That is, we can begin to understand neural networks, real neural networks, for the first time because we know what they're controlling. Perhaps we can do better than training up artificial neural nets in the future. Then we can take from our dynamic model, we can go into the lab and measure the actual muscles themselves in order to test our hypotheses about function. And you'll see the muscle there when we connect it to a special thing called a lever so we can test our ideas. There's the muscle. All right, so much for roots and rules, the basic research. What about relevance with respect to application? After an intense period of reductionism in biology, DNA, genes. We're entering an age of integration, not only within biology, but among biology, engineering, math, computer science. What's required for true biological integration and inspiration? Well, first, I think we're going to need a collaboration among biologists. At Berkeley, we dissolved 5 departments and formed one department of integrative biology. Second, we need to capitalize on the wealth of design ideas, not only in nature, but sitting in our dusty old research museums. Design ideas from museums like the Museum of Vertebrate Zoology at Berkeley with a tremendous number of wonderful specimens. Design ideas from plants in herbaria. Design ideas also even from extinct animals in the Museum of Paleontology. It's a gen bank waiting to happen with wonderful, amazing structures. Third, we need a faculty that is interested in biology but can talk to engineers and computer scientists and others. And finally, we need the technology in order to quantify the structure and the motion. We've produced this Bio-Ape Center at Berkeley in order to be able to do this. The structure and the motion of real organisms can inspire education, robotics, computer animation, and medicine, and a variety of other things. Let me tell you first, just mention one project we're working on with respect to education. My mystery story is only one of many stories. Biologists have thousands of exciting stories to tell. But we must change the way we're doing this. Professors, I think, can no longer act as giant fluorescent highlighters of what to memorize in these growing encyclopedias that we call textbooks. We should make databases of electronic case studies that don't focus on the facts, but focus on the process of critical thinking that leads a student from personal discovery toward the ability to make universal discoveries. We can also inspire robotics and animatronics. Mark Raper at the MIT Lab has been doing this for many years. For example, here's the pogo stick. Here's the spring mass model. He's going to talk in actually the next TED conference. His robots are amazing. They're still the best mobile robots that have ever been built. They move like animals. And you feel sorry for them when they fall down. You have to see these.
We're going to try to have some of those in New York.
Oh, wonderful. We also have done a project with Rockwell and IS Robotics, inspiring the design of an ALUV, an autonomous legged underwater vehicle that's inspired from a crab. Now, what these robots are able to do, here's the robot named Ariel. What this robot's able to do is find landmines that, in fact, kill thousands of people every year, unfortunately, mostly children. Like crabs, they're truly amphibious, so they can go in the water. They can clean up toxic wastes in places that humans really shouldn't go. Now, the design ideas for leg movement, for the motor placement, for the shape of the body have come from our work on animal locomotion. The same is true with the decentralized, distributed type of control systems that we find in animals like insects. I'm convinced that smaller versions of this will be able to explore outer space, and you'll see this. They'll be able to be a personal scout for you, if you want one. And eventually, we'll even be able to monitor your insides. I think quantitative biology is just beginning to inspire computer animation in a real way. Again, a collaboration with Mark Raper, at this time from his company called Boston Dynamics, shows we've designed a simulation of a cockroach, of insect locomotion. Now, this is not just a cartoon. It's not just the motion. The physics is in this program, the gravity, the inertia, the ground contacts. And these dynamic models are tremendously helpful in understanding biology. We can do experiments that we just can't do with the animals. In fact, we can design organisms that don't exist and ask why. Now, clearly, these models can also be used to revolutionize, I think, computer animation. Boston Dynamics has shown that an understanding of both the dynamics with the control systems will allow you to generate animation from higher level commands rather than by intensive, laborious keyframing approaches. I'll tell you now that I'm sure that you will see animated bugs in some movies in the next few years. Quantitative biology can also just beginning to inspire medicine. For example, Hugh Hare at Harvard works on springy shoes. There's the spring. This is the same principle. Things bounce in nature when they have legs. Why not use it in cases like this? In particular, put it in sneakers for handicapped individuals who have lost their natural springs and give them back this capability. Another example from medicine includes artificial muscles. Here's a robot we built. Those black tubes in the back are actually muscles, but other labs focusing on this here are really making progress using pneumatic muscles, shape memory alloys, wonderful oscillating wafers of various materials, and fibers that are sensitive to chemicals, fibers that actually contract very much like real muscles. I think the next generation of robots will be smaller than your fist, but larger than a sugar cube. They're going to be called mesoscopic machines, and they're going to have MEMS, actuators, and sensors all over them. And in a way, I'm not totally surprised. If you look at nature, the typical animal is a mesoscopic machine. It's an insect. Finally, the ultimate integration, part biology, part robot, some work from the University of Tokyo. This is a male silkworm moth with an extraordinary sense of smell. It's picking up the scent of the female now. It's lost it, and now it does a searching behavior until it finds it again. No human sensor could be better. Its specialized antenna can detect 1 molecule of female pheromone in 10 to the 15th air molecules. The Japanese have cut it off and have glued it onto a robot. And those are the antenna, and they're giving it the programmed behaviors of the animal. So here it's searching for the scent. It's delivered by that tube. When the real moth antenna pick it up, it follows it, just like the animal does. We really are entering a new age of integration, and I'll tell you that it's just the beginning. Thank you.
Fantastic. Thank you so much. Thank you. There's some gifts there. I'll get them right after the thing.